Hey everyone, it's been a while since I've seen a really good binary tree question, but I just came across 545, boundary of a binary tree. Essentially, we just need to traverse the tree or capture the boundaries of the tree. So, I mean, it's pretty much as simple as it sounds. It's you capture these are the boundaries of the tree, so we just need to print it out in this following order, right? So if I was looking at it from the top, and then if pretend I was circling the tree and which nodes I need to just capture which nodes I was seeing, and then return that. So let's just read to just make sure. So the boundary is a concat. But the boundary of binary tree is a concatenation of the root, the left boundary, the leaves ordered from left to right, and then reverse order of a boundary tree. So pretend you're just literally circling the tree and taking note of what nodes you saw. So the reason it's interesting because I think we need to, yeah, usually you see questions like vertical order traversal, you see level order traversal, DFS, BFS, but this one we might need to make a mix of both. What I'm thinking is, or maybe it's a simple level order traversal. So maybe we do this, we pop that into the result, because the expected result right here is, right? So if we go this way, we pop 1, and then we pop 2. Or maybe we make, sorry. Maybe we make a few different lists. Make, maybe all we need to do is a left and right. And then bottom. So maybe this is all we need to do, and then we just do a regular BFS. So 1, it's the first one on that level, so we throw 1 here, and then we go this way, and the first node we see in each level we pop into the left, and then the very last node we pop it into the 3 or into the right. 4, 6. 4. Maybe we need to add this in. 6. Like if we have a queue or something. Then on the last level, if we know we're on the last level, how do we know when we're in the last level? I mean, let's just keep track of the last level as well. So we keep track. Okay, we put 7. We add to the front of this queue. Sorry. But then 8 and 9, we just literally push into the bottom. These are the middle ones. And maybe we just keep cycling bottom. But essentially, finally, to build our result, we take the whole left side. 1, 2, 3, 7. Then we concatenate 8, 9 to it. 9. And then after, we take whatever on the right. Then what's the answer here? So that's see what the expected answer is. Yeah, I think it's simple as that. Just level order traversal. But we need to, every first element we pop into our left, every last element we pop into our right. And then we just keep, for each row, we kind of save the intermediate ones. But then we keep replacing bottom. Yeah, okay, let's do that. So we're gonna do a simple level order traversal. Or no, what? Oh no, this might be harder than that, because if we do a level order traversal, Sorry. Sorry, my throat is a bit itchy. Oh. Because this one doesn't work the same. Pretend we have 1. We need to skip 2 because that's on the right side. Interesting. So this one's actually 1, 3, 4, 4, 2. The left boundaries are set. The root's node's left child is in the left boundary if the root node's left child is in the left boundary. If it does not have a left child, then the left boundary is empty. Oh, okay. If a node is in the left boundary and has a left child, then the left child is the if a node is in the left. Wow. Okay, this is kind of confusing. If a node is in the left boundary and has a left child, the node is in the left boundary and has a left child. Okay. If the node is in the left boundary, has no left child, but has a right child, then the right child is in the... So if we remove this, okay, I think we just need to ignore the root and then just figure out the left side here. Then we need to ignore the right. Then we need to ignore the right or left here, and then just find, and then just do a we can do I see. Okay, so we just need to do a view the left side. We need to pop this out and then view the left side. Pop this out and view the right side. And then we can figure out how to do the bottom at the end. So that will probably get us the right left child and the right child. What's happening here? Hopefully my... Yes! One of my builds are passing at work. Love it. Okay, we just need to ignore the root, then just capture the left child. And ignore the root here and then capture the right child. And then we'll figure out the bottom level at the end. Okay. Oh, maybe we can just still do a level or a traversal. What if it's left? So, like, I see. Yeah, we could still probably do a level or a traversal, but if it has a left, you just ignore it. So, do 1. Okay, we'll just do the same level or traversal. We'll have our left and right, and then we'll have our bottom, which will cycle. And then we'll do empty has left boundary equals root dot left has left if true if root dot left, else false, has right true if has right true if root dot right, else false. Then what we're gonna do is we're gonna just do our regular level order traversal. So let's do a queue from collections. We'll say the right side we need to append backwards, so that's a queue. But we'll also add a queue here. Then we'll have our result, or we'll build up our result at the end. We'll say queue. So we have our queue, and we're going to initialize the queue with just the root. We'll say while length of queue is greater than 0. While the length of queue is greater than 0, we're going to do our level order traversal. We'll be like for this in the range of length of the queue, we're going to iterate. We're going to set bottom equals to this. We're going to say for this in range, what we're going to do is we're going to pop out the element candidate equals q dot pop left. If index and has left. If the index equals to 0 and we actually have a left, let's just do root. Kicking out some deployments. Q dot right. So we don't even need to manage the root, right? So we initialize the root's already in there. That's already going to be in the left. So for index in the length of queue, if we pop a candidate, if it's equal to 0 and has a left, we say q, or we say left dot append candidate dot value. Elif index equals to length of queue, or here. If it's the last index, we say right dot append left candidate dot value. If it's in none of those, it's part of the row. So we just go bottom dot append candidate dot value. And we just do a simple add the neighbors. Add left first q. left, print right, print bottom. Awesome. So we do our result. Then we say result equals left, pretty much. And then we say for element in bottom, we say result dot append element, and then for the right side, we also say from the right side for element in the right side result dot append element, something like that. We just have one. Oh. What's happening here? So this is the tree. Let's debug. This is what my output was, and this was the expected. I'm missing a value. Oh, that counts as, oh, you need the bottom view. Catch that. You need the bottom view, not just the bottom row. You just need to pop up all the leaves. Yep. Just don't replace bottom there and just capture all the bottom. What? Okay, there's a bunch. Oh, I'm not capturing the has right. If please work. Just spamming these test cases now. What's wrong with this now? Why didn't I pop the Lee cell first? Why was that part of the right side? We need to, okay, we have to do the thing where we ignore the root. We have to do the thing where we ignore the root and just figure out the left side and then the leaves. We have to do a left side. Yeah, we need to ignore the root and then do a left side. So left. A lot of edge cases here, Dev. So we have init. Let's just initialize all these up here. We'll just copy over this code for level order traversal. To clean it up. So we do if the root is none, we'll do self.top.end. So we get the node. Left. So left default is that. So if so we're gonna do if we're viewing left, we're gonna do one thing. So if we're viewing left, we're just gonna print out if left, then we'll go if the index equals 0, then we append it to left. Otherwise, we're looking from the right side, and then we're going to be looking at the last index. So the top. Let's do this. See what this says. Top, left. How did the left get there? It should just get 4 because we just have root. How's it getting 3, 2? Oh, okay. Sorry. I need to. One, 3. One, 4. Okay. It's looking good. Self dot right -1 -1 -1. Go reverse order. Please work. Are you returning nodes? Oh, okay, I see. We already extracted the value. Woo! Oh my gosh. What's going on? What is going on? What? What? Why didn't I put 53? Or why didn't I get 33 there? Why didn't I get 33? Why didn't I get 33? You get like a bottom side view. Maybe I should have just like built out a full matrix. Okay, for the bottom side view. Let's throw in their column first. So we know what column they are. Wait, why would 33 go first? Zero, -1, -2, -1, 0, 1. -2 or 0, -1, 0. Why would it see 33 first? What? This question is so dumb. Okay, now my problem is just ordering the 0. So all the leaves. This does not make sense. Oops, let me fix that thing in the back. This is so whack. Okay, let me read what the bottom is. The leaves from left to right. We are looking at the leaves from left to right. Do we need to start from the bottom? When does 78 appear? Bruh. This question's so dumb. Like why is it gonna pick 53 over this? How should we view it? So we okay, this is a leaf. Then how do we get the leaves in this order? See if this is a sub question. This. I'm just gonna do a DFS to get the leaves. I don't care. Do a regular DFS. Yeah, we could do a DFS to get the regular DFS to get the leaves. Let's not even handle leaves here. So we're gonna look at the left first. DFS. Self.dfs node dot left. So we're just gonna do a regular DFS because that will actually capture it. Like if we go left, then we go this side, leaf, leaf, go this way, leaf. So if .dfs. Okay, what's bottom here? Oh, okay, sorry. The way I'm adding scene was wrong. Scene. hit submit. Let's see what's wrong. What's happening? Missing values. And now the tree is so massive I can't even see it. What kind of edge case is this? Why did they just make a smaller one? Like, bruh, what is that? Can you at least give me the output for real? Bro, that's so terrible. Why don't they just allow a little scroll? Okay, I fixed some of it. I need a... Dude, this tree visualizer sucks. Who made this app? What broke? Bruh, I can't even visualize the freaking tree. Dude, this is why people give up on Leetcode, huh? I'm really going through it right now. 6, 4, 12, 4. Dude, why can't Leetcode just visualize the tree like fully? How hard is that feature? Do I need to go? I might drop a video. I'll just implement that whole feature. Like, bro. Bro, what the hell? Dude, this is so terrible. Dude, if I can't even visualize the tree, I can't even see why they're picking that. Oh, I'm gonna actually lose all my hairs on this question. Alright. How do we get the leaves? What? Screw this question, man. This is so annoying. The solution, man. How did they get the leaves? What? This is all I need to do right here? What? Guy kind of did the same thing. Does this actually work? What's wrong with my code? I'm not stopping till this is done, man. Bro, what the hell's going on? I have no idea what I fixed, but I only have one thing wrong now. What? So I get the top. I grab the left side. The left side is root dot left. The right side is root dot right. Oh, I need to look at this. I need to do this in a whole different way. Why am I missing a value? kind of hard to debug this thing without a proper tree. Yep. Rip. I can't figure this out. Should have got added, right? Use the last index. Okay, it's mad that I'm added. Alright, I need to come back to this, man. I got folded. Holy crap. Okay, my cycle completed. Alright, I gotta pause this and grab my laundry. I mean, I'm just gonna end this video. I took an L. I need to approach this in a different way. I tried to, like, just shotgun my solution in, but yeah, I just literally took an L after how many questions I've done already? Disappointing, disappointing. Not a good start to the day. See y'all in the next video.